In this work, we present CppFlow, a novel and performant planner for the Cartesian path planning problem. The proposed planner finds valid trajectories up to 129 times faster than current methods, while also succeeding on more difficult problems for which others fail. The goal of the Cartesian path planning problem is to find a trajectory for which the robot's end effector stays along a provided Cartesian target path, the joints stay within their limits, the motion is sufficiently smooth, and the robot avoids any self-collisions or collisions with the environment. This problem is common in many industrial applications such as welding, milling, drilling, and spraying. For 6 degree of freedom robots, this is a fairly tractable problem, because there's a fixed set of possible families an IK solutions can fall under, for example, elbow up or elbow down. For redundant robots, the problem becomes much more difficult, as you can no longer just find a sequence of IK solutions with the same family. In more detail, in this problem we are given a description of the robot and a target path y. Y is a sequence of n Cartesian poses where n is the number of time steps in the path, which the end effector must pass through. We can think of them as a discrete representation for some continuous path through SE3. We're asked to return a trajectory xi, which when executed will have the end effector reach each of the poses in the target path. Time parameterization is omitted. It is assumed that this is handled by an external system. CppFlow is evaluated on 13 different planning problems and 3 different robots. We use the Panda and Fetch robots. The Fetch robot has a prismatic joint which lifts its torso and arm. We call the robot fetch.arm with this disabled and fetch.full with the prismatic joint enabled. Other state-of-the-art methods including Torm and Stampede are also evaluated to provide a comparison. The proposed planner borrows from 2 different paradigms, classical algorithms and modern learning methods, in order to get the best of both worlds. The learning method we use is ICFlow, a learned generative inverse kinematic solver which is able to efficiently produce promising entire candidate solution trajectories in the GPU. We rely on search and optimization for the classical methods to get precise solutions. This component generates approximate motion plans by calling ICFlow. First, k latent vectors for ICFlow are sampled, where k is a hyperparameter. Next, we compose a batched input by pairing the target path y with each of the k latent vectors. Each of these latent vectors are repeated n times. We then call ICFlow using this batched input. The k times n IK solutions are segmented according to their latent vector, resulting in k approximate and diverse motion plans. On the right, we can see 3 such approximate motion plans for the Panda Flappy Bird problem. K is 3 here. Notably, all 3 are different from one another, which is a desirable result. Next, the motion plans are checked for any self or environmental collisions. In this work, links are represented as capsules and objects are represented as cuboids. The collision detection problem is framed as a quadratic programming optimization problem and solved using an active set method. A search procedure is now run on the motion plans. A globally optimal trajectory is found by searching through a graph constructed from the motion plans, where optimality is determined by the MJAC metric. MJAC is the maximum absolute change in joint angle across 2 time steps during the entire trajectory. In practice, a robot will move smoothly when executing a low MJAC trajectory. 50 motion plans are shown in blue on the right. The red line is the solution found by the search procedure. This trajectory is optimal with respect to MJAC and is collision-free. Here we can see MJAC as a function of k for 3 different problems. As k increases, the MJAC reduces. This is a positive result which validates the approach. It also indicates that the proposed method scales well with compute, which is a valuable property to hold in the era of ever-improving GPU performance. Lastly, an optimization routine is performed. The optimization problem is framed as a nonlinear least squares problem and solved using the Levenberg-Marquardt algorithm. This algorithm uses an error residual and asks for the Jacobian of this residual with respect to the optimization variables, in which case is the trajectory itself. Here we define trajectory length as a cumulative change in configuration space across a trajectory. The optimizer continuously improves its solution until stopped. Thus, CppFlow is an anytime planner. This is shown on the right. As the number of optimization steps increases, the trajectory length continues to decrease. There are 4 sub-objectives included: pose, configuration differencing, and self and environmental collision avoidance. Pose keeps the end effector along the reference path. Differencing ensures the trajectory has a low MJAC. The collision error terms prevent penetration between collision geometries. A non-stationary objective is employed to avoid local minima. A simple policy decides the objective at each step. Pose error is used exclusively until the maximum positional and rotational errors are below their respective thresholds. Once this is satisfied, the remaining loss terms are used to ensure a smooth and collision-free trajectory. CppFlow quickly generates smooth, collision-free trajectories such as the ones shown here. We validate the return trajectories on real hardware with the Franka Panda arm. This demonstration is for the Panda Flappy Bird problem. CppFlow is evaluated along 3 axes of comparison: planning success rate, time to a valid solution, and trajectory length over time. For the first 2 axes, a valid trajectory is one for which the constraints of the problem are satisfied. 2 other methods are compared against: Torm and Stampede. Planning success rate is defined as the percentage of runs which return a valid trajectory after a given amount of time. In our case, both 2.5 seconds and 50 seconds are tested. For this metric, CppFlow performs better than all other methods. Time to a valid solution is defined as the average time before a valid solution is found. Valid solutions are generally found within 1 second and often within 600 milliseconds. For this axis, CppFlow performs significantly better than all other methods. Trajectory length convergence is defined as the mean cumulative change in configuration space of the latest valid trajectory found before a given amount of time has elapsed. For this axis, CppFlow performs comparably to Torm and better than Stampede. The quantitative results indicate that CppFlow performs better than all other methods on 2 of the axes, while performing comparably on the third. Thanks, and please read our paper for further details.